Greetings and welcome to our next video. This one's on osmosis, and you see there it's like diffusion, but it isn't. People tend to confuse osmosis and diffusion, and hopefully in this video we'll make sure you're really clear on the difference between osmosis and diffusion. So what is osmosis? Osmosis refers to the movement of water. Key difference is the movement of water from a higher to lower water concentration through a selectively permeable membrane. So there's some important pieces here. So again, water, we're talking about water's movement, not solutes movement. And we're talking about from a higher to lower water concentration through a selectively permeable membrane. So again, some key differences here, water and the membrane. Or you can think of it this way as water moves from a lower to higher solute concentration. And again, here's where people get a little bit unglued with osmosis. So my suggestion is you focus on one or the other. Either you focus on water's movement going from a higher to a lower water concentration, or from a lower to a higher solute concentration, because they really do mean the same thing. Let's look at this example down here. So over here, these little balls here represent water molecules, and these bigger green dots represent solute. It could be sugar, it could be salt, it could be anything. So here's a key difference. We have a membrane that is selectively permeable. This has very small holes in it, and these holes do not let the solute move from here to there or from there to there. Notice there's a concentration difference. We have more solute on this side than that side. If we didn't have this membrane here, what would happen? The solute molecules would bounce off one another and would bounce off water, and eventually the solute would evenly distribute at equilibrium throughout this entire container. However, we have a membrane, and we have a concentration difference. The solute can't move from higher to lower concentration. It can't do this because it's too big to pass through those holes. This membrane is selectively permeable and won't let it pass through. However, water is small enough to pass from here to there. And notice again, on this side we have high water and low salt. Or we have here high solute and low solute. Same thing. But the question is, what's water going to do since there's a concentration difference? Water is going to bounce around, and since water can pass through this membrane, eventually more water moves this direction than that direction, and we end up with more water molecules here to balance out the solute, fewer water molecules here because we have less solute. So this is what happens in our artificial membrane system we have here. Water goes from a higher to a lower water concentration, or to where there's more solute. Now, this is, again, artificial. What if we're talking about in a real cell membrane? Cell membranes have special channels that water can move through called aquaporins. Aquaporins were just discovered not too long ago, and the people that discovered them won a Nobel Prize, that water molecules can pass through membranes, basically through their own channels, own protein channels, called aquaporins. So let's look again at this example. Here again we have these yellow dots represent solute, the blue dots represent water. Please notice there is water that does move from one side to the other. Water is bouncing around, and so some water is going this direction. However, most of the water is going to be passing through these channels, and it's going to be going here. So over time, we're going to see more water flowing. The net direction of water movement is going to be that way because water is moving from a higher to a lower water concentration, or from a lower to higher solute concentration. So that is, again, the difference with osmosis. Solute is not moving because of the membrane. Now, there is a pressure called the osmotic pressure that is created as water moves here, as water moves here, as water moves here. If we wanted to stop water from moving, we'd have to basically put a back pressure, push it back the other direction, and that's referred to as an osmotic pressure. And we'll see that more as the course goes on. We'll see examples of the osmotic pressure and why that's important. So a really important question, and one that I think is really critical to understand, is, okay, seriously, why does water move at all? Why does a solute not move? This will show you, this is the best picture I can find of this. Here is a sodium ion. Okay, it's an ion, positive charge. Notice what happened here. All these water molecules, because they have negatively charged oxygens, because again, oxygen is very electronegative, it pulls electrons close to it. So all of these are kind of hanging out with this sodium because of sodium's charge. If you want to think of it this way, these water molecules really can't move the same way that water molecules that are unattached can move. That is, if you want to think about all of these kind of stuck to it, all of these kind of stuck to it, all of these kind of stuck to it, these water molecules can't move. So now we have even more water molecules here that can move this direction and maybe eventually stick to a sodium than water going the other direction. In other words, we have this what are called these hydration shells. Water is moving where there's more stuff and sticking to it, so that water really isn't available to move over time, and more water, therefore we were going this direction over time than that direction. So the reason, again, that water is moving is not because it wants to. Please don't say, water wants to go. Water doesn't want anything. Water is bouncing around randomly. If it's sticking to stuff, then it can't move the same way that water that isn't sticking to something can move. So we have these things called U-tubes. You may have heard of it as this little site on the internet, but think about what happens in these U-tubes that have these membranes here that are selectively permeable. These membranes won't let, in this case, sugar molecules go from here to there. Why would sugar go from here to there? Because of a concentration difference. However, it can't because of this membrane. We say it has on this side greater osmolarity, that is, more concentration of stuff on one side than the other. So what happens over time because of this? Well, because water molecules are sticking to the solute here, over time what we're going to see is water molecules are going to go net that direction more over time, and eventually we even see this difference in water level. And you're thinking, that can't exist because gravity won't let that exist. That exists because of that pressure of water that's going through that membrane over and over and over again, more this direction than that direction. So over time we see that difference. And now if you want to think of it this way, let's pretend we started over here with, I'll make up a number. This is 70% water on this side, and it's 90% water on this side. Okay, you could also say it's 30% solute, and it's 10% solute. So there's a concentration difference. By the time everything gets done moving, perhaps now this is closer to 80% water here, 80% water here, 20% solute here, and 20% solute here. Over time, we will reach an equilibrium because of the net movement of water. Okay, so now this brings us to a topic that does tend to bother people, tonicity. Tonicity refers to a comparison of the concentration on either side of a membrane. So what we mean by that is, in a hypertonic solution, let me draw this for you. Okay, if I have a cell that's in a hypertonic solution, so that means it's got some things inside of it, it's got some solute, but let's say it's in a tube, and this tube has lots and lots and lots of solute in it. Okay, so if I want to compare the solute concentration, sorry for my great drawing here, if I want to compare the concentration, there is more stuff on the outside than inside. So this solution is hyper, that is more than, tonic than the cell that's in it. So this is a hypertonic solution. There's more stuff in the solution than in the cell. Okay, we'll talk about what happens to water in a second. If I have another cell, and this cell's got quite a bit of stuff in it, stuff could be calcium, magnesium, sugar, salt, you name it. But outside, it's got very little, relatively speaking, then this solution is going to be hypo means less tonic than the solution inside the cell. Isotonic would be, it's the same. If we had a cell that had, let's say the cell has 3% stuff in it, and the solution that's in has 3% stuff in it, then iso means the same. Isotonic would refer to that cell solution. The solution around that cell is isotonic. Now, really important, what happens to the movement of water in each of these cases? This is the way you think about this. Water always goes, always, where there's more stuff, where there's more solute. So in a hypertonic solution, what happens to the water? Will it go into or out of the cell? It will go out, more so than coming in, because there's more stuff out here for water to stick to. So in a hypertonic solution, the cell would lose water. In a hypotonic solution, the cell is going to gain water because there's more stuff on the inside. In an isotonic solution, there's going to be the same amount of water going in as coming out. Okay, what's the relevance of all of this? Cells are going to live or die depending upon concentration of stuff and the movement of water. Here is just a little silly video of this. Okay, here is a hypotonic solution. So the solution is hypotonic, so that means that what's going to happen to water? Okay, water is going to go in where there is more stuff. Okay, isotonic means it's going to come in and out at about the same rate. And I don't know why my video is not working. Maybe I'll try here in a second. But hypertonic means there's more stuff out here, so water will leave the cell. Let me try this. See if you can see it again. Here we go. So notice on the hypotonic side, it's gaining water. On the hypertonic side, it's losing water. And again, this refers to the solution. It refers to the stuff out here. So hyper, water is leaving the cell. Hypo, this water is going into the cell. Okay, just some examples of this, and then we'll wrap up. Does this matter at all in the body? Do we really care about osmosis? Yeah. You just saw an example with the blood cells. Red blood cells are anucleate. That means they don't have a nucleus. So they don't have protein channels that can control whether water goes in or where water goes out. So water can go in or out based purely on solute concentration. If the cell has a lot of stuff in it, water goes in. If the solution around the red blood cell doesn't have much water, or has a lot of water rather, water will leave it. So that matters what kind of concentration. So if someone's dehydrated, what's going to happen to their blood? It's not going to have as much water in it. Okay, what's going to happen to the water in their blood? It's going to tend to want to go into the cells because they have more stuff in them. And you can see already we're going to have a homeostasis issue. And that gets to this point here. Water is critical, and the stuff around the cells are critical to the movement of water. So if I have, again, depending upon the concentration of stuff I have, will water go into that cell or will it leave it? That's a huge issue in things like electrolyte imbalances. I give you this example over here to go with the kidneys. In the kidneys, you have about 1 million of these tubes called nephrons. And what passes through these tubes will be stuff that could be urine. But as solution moves through here, we're actually going to pull water out of the nephron by osmosis, and you're going to recapture that water to go into your bloodstream. You filter out a lot of water in part of your kidneys, and if you did not recapture that water somehow, you'd be peeing out gallons and gallons of water a day. It's not a very good thought. So water is pulled back out of your nephrons by osmosis. Essentially out here, you have lots and lots and lots and lots of sodium. And that draws, that attraction pulls water out, and then it goes into your bloodstream and you carry it away again. The last example here is you see these tiny gaps between our cells and our intestines. we have ways of basically moving water along with nutrients to help the absorption of our minerals and nutrients in our intestines. So I'm going to wrap up here. We're getting long. So people say, yeah, Mr. B, I'm going to learn A and P. I'm going to learn it by osmosis. And here's Garfield with books all over him. Obviously, this is not osmosis, right? It's not osmosis because this is not water movement. He's trying to imply he's going to learn by diffusion from a higher concentration to a lower concentration. But whenever someone says, oh yeah, I'm going to learn by osmosis, I'm going to put the books under my pillow and I'm going to learn by osmosis. That is not osmosis. That is diffusion and it doesn't work anyway. Okay, that's it for this video. Thanks.